In this mini lecture, I'm going to talk about exponential and logarithmic equations. Now, to start with exponential equations, those are equations where the variable is in the exponent. So if you look at this equation here, for instance, 2 to the 2x plus 1 equals 7, my variable x is in the exponent. And that makes it difficult to solve the equation because I sort of have to get the exponent, the variable out of the exponent to be able to solve for it. And there are a couple varieties of exponential equations. We're going to start with this solving exponential equations with equal bases. So that's where I have the same base on both sides of the equation, basically. And that's this first equation down here. I've got 2 to a power and 2 to a power. Essentially, if two expressions are equal and they have the same base, the only way that can happen is if their exponents are equal as well. That really comes from the fact that the exponential function is 1 to 1. And so to have equal outputs, I have to start with equal inputs. And so we get this property. If I have b to the m equal to b to the n, I can essentially ignore the bases and just set the exponents equal to each other and get m equals n. So I can do that on these two examples here. This first one, I have equal bases of 2, right? 2 to a power and 2 to a power. So I can just set the exponents equal to each other. So 2x plus 1 equals 7. I'll subtract 1 from both sides. That'll give me 2x equals 6. And when I divide by 2, I get a solution of x equals 3. Now, in this second equation, I don't have equal bases. I have 2 to a power on the left, but I just have 8 to a power. There's really a 1 above the 8. 8 to a power on the right. And so what I need to do is figure out, is there a way I can rewrite this equation so that I do have equal bases on both sides? And in this case, that's certainly true because I can rewrite the 8 as 2 to the third power. So I would get 2 to the 4x minus 9 equals 2 to the third power. 2 times 2 times 2 is 8. Now I have equal bases on both sides, 2 to a power and 2 to a power. So I just set the exponents equal to each other. 4x minus 9 equals 3. I add 9 to both sides. That gives me 4x equals 12. And when I divide by 4, I get x equals 3. Now, obviously, this is a coincidence. We got x equals 3 both times, but that's not always going to be true. Also, it's not always going to be true that I'm going to be able to get equal bases on both sides of the equation like I was able to do in these two problems. So that's the second type. If you can't get bases equal to each other, I can usually solve these kinds of equations by using logarithms. Like here, 3 to the x equals 18, I can't rewrite 18 as 3 to a power. If it was 9, I could write 3 squared. If it was 27, I could write 3 cubed. But there's no way to do that with 18. So here's some sort of instructions we can use, like a series of steps we can use to solve an exponential equation using logarithms. We try to get the exponential stuff by itself. So here that's already happened. I've got 3 to the x by itself. Then I'm going to take the logarithm of both sides. Now, if you happen to have 10 to a power, like here 10 to the x equals 13,000, we might want to take log base 10 of both sides. Otherwise, your author suggests to use the natural logarithm. Natural log, that's log base e. Then I'm going to use the power rule. You'll see how that works, and then we can solve for the variable. So in this problem here, I've already got the exponential expression isolated, right? I've already got 3 to the x by itself. So then I'm going to take the log of both sides. So natural log of 3 to the x equals natural log of 18. Now the power rule says if I have the log of something to a power, I can bring that power down in front. And so this x can come down in front of that logarithm there. I get x times the natural log of 3 equals the natural log of 18. And then to solve, I just divide both sides by natural log of 3. And if I do that, I get x equals the natural log of 18 over the natural log of 3. Now, there's no way of simplifying that. I can't cross out the natural logs. I can't say 3 goes into 18 6 times. The natural log of 18 is some decimal. The natural log of 3 is some decimal. It really says, natural log, we really have log base e. So this really says e to what power is 18? And that would be some decimal that I don't know. When I do some example problems later on, we'll talk about how we could use a calculator to get a decimal approximation. This we call an exact solution. If I would go and make this a decimal, then I would call that an approximate solution. Okay, so if we leave it in terms of logarithms like this, that's called exact. If I do it on a calculator and get a decimal, I have to round, and then that becomes an approximate solution. Okay, so those are exponential equations. Now we're going to talk about logarithmic equations. In logarithmic equations, the variable is inside a logarithm, like we have here. In this equation, sort of in the middle, log base 2 of x minus 4, x is part of a logarithm. Or here at the bottom, log base 3 of x plus 2. Typically here, it sort of depends if you have logs on just one side of the equation or on both sides of the equation. What we have here, this first case is how I can proceed if I have the log on just one side of the equation. What we have down here is if we're solving with both sides of the equation. And in general, again, these are some steps you can follow. If I have the log on one side of the equation, I want to try to get just a single log on one side and a number on the other. Then I rewrite the equation in exponential form, and I solve using the techniques we had in the last section if I need to, but I solve for the variable. What is important here, the log has a domain from 0 to infinity. You can't take the log of a negative number. So if I came up with a solution of x equals 1 for this equation, if I plugged in 1, I'd get 1 minus 4 is negative 3. And I'd have the log base 2 of negative 3. And that's not allowed, so I would have to throw that solution out. That's not going to happen here. When I do some examples later in some other videos, you'll see that happens sometimes. So to solve this equation, step 1 has already happened. I've got the log by itself equal to a single number. So then I go ahead and I rewrite this in exponential form. Remember, to write in exponential form, this is my base. The base stays the same. This is my exponent. The log is equal to an exponent, and then that's going to be the result. So I would get 2 to the third equals x minus 4. 2 to the third, 2 times 2 times 2 is 8. And then I'll just add 4 to both sides. And I get that x is 12. I do want to check that. If I plug 12 in for x, 12 minus 4 is 8. Log base 2 of 8 is 3. I don't run into any trouble with log of a negative number. The final type of equation we're going to look at in section 4.4 here, solving logarithmic equations when I have logs on both sides of the equation. Again, like the exponential function being 1-to-1, the logarithmic function is also 1-to-1. So that means if I have two logs that are the same, if I have equal outputs, then I had to start with equal inputs. So I can essentially just equate what I'm taking the log of. How that works down here, I have a log of a log, right? Log base 3, log base 3. I just set what I'm taking the log of equal to each other. So I get x plus 2 equals 8. I subtract 2, and I would get x equals 6. Again, we should at least check to be sure that that doesn't lead to me taking the log of a negative number. If I plug 6 in for x, 6 plus 2 is 8. That's not negative, so I would be set.